Today I'll be talking about some kind of general view, I think a general view about the field. Very related, I think, match with the graphs. That kind of graphs is a kind of key object here to our discussion, and an interesting way of encoding assumptions needed to do causal inference. And we are kind of very excited. What? Yes, sorry?
Sorry, just
yeah, okay. We are very excited to, with recent breakthroughs that happen in AI, which the way that I interpret is like systems are able to perform extremely well in making predictions in high-dimensional settings. It has been ongoing for a few decades, and now many things start working. We're able to scale up at some kind of crazy dimensions, which leads to some sort of emergence and many good things happening. In particular, there has been huge progress in fields of NLP, computer vision, and reinforcement learning. Then some kind of perceptual capabilities, vision, and language, and some kind of decision making that is related to reinforcement learning. I think most of you may have heard about it. That is the machine learning way of doing sequential decision making. There are other fields that have different names for that. Applications are everywhere, this is just some of them, from medicine to business, agriculture to space exploration, and that's kind of really great and exciting. Now the question that I would like us to ask, and I ask myself and in my group, is like, does this mean that we are done? And done here in the sense of, it's more, if you scaling more and doing a little bit more of the same. Maybe you took a few dozen or a few hundred PhD theses, maybe a few $1 billion in terms of compute primarily, and eventually we'll get there. We'll have the most general type of AI that we want. And in order to try to answer the question, just for the sake of exercise, I would say assuming that we have infinite amount of computation and data. Stick with me. Let's try to do the the thought experiment in some way, Gedanken experiment. And if not, what's missing? Now, I'd like to see the other side of the coin here in terms of the excitement. There are still pretty much some fundamental challenges here related to AI. Current AI systems suffer from a lack of explainability capabilities. There's very low understanding. We like to formalize that. We have maybe some mathematicians in the room. We like to have some notion of understanding. And these systems, in general, are not performing very well explanations, at least explanations about the world, I would say. There are two types, but I will defer for now, about the world and about the system itself. But anyhow, they are kind of unfair and unethical decision-making potentially there. They are very data inefficient. Sometimes you need billions of data points to do something that humans could do in a much smaller scale. And they are very poorly generalizable. They can kind of break very easily. If you are an expert, you can kind of craft examples that the thing will break. And also they lack some notion of controllability in the sense that not even the people that are, and some people is kind of PhDs here, that when they work to these companies or they're at Columbia, no one has idea what the systems are doing in reality. You have no way of getting inside some kind of complex latent space, change something, and making the system go in some direction. Very hard to do that. Now, I'm not the only one noticing that. This is just, we can kind of Google at random meaning in general, and say, this is just from CNN that I got recently. AI could pose extinction-level threat to humans, and the US must intervene. State Department Commission report warns. This is another one from the Nature briefing saying AI and robotics briefing. There is a 5% risk that AI will wipe out humanity. The number is cute, right? It's like, what's this number mean? But still, I would say there's a non-vanishing probability of something potentially catastrophic or bad happening. This is humanity face a catastrophic future if you don't regulate AI. I have my own opinion, but in any case, godfather of AI, Yoshua Bengio says. Then there is some kind of recognition again. I'm not the only one saying that there are potential problems there. We can discuss what is the degree, how high you are screaming, what is the right balance, and what. but still there is a recognition that there are problems. On the technical side, this is kind of a thorny, long-standing problem, some of them. I don't know, interpretability and explainability, unfair and unethical decision-making, data inefficiency or data hungry, lack of robustness and generalizability, and so on. This is going on for some time. It's just the scale is crazy at the moment, which anyhow, it seems to raise more red flags, right? People can scream a little bit or substantively higher. And the question that I ask myself is like, do these problems have anything in common? Now Elias here, EB observation, I think it's quite natural, my biased way, but at the core of these challenges is the absence of some kind of robust causal reasoning. Then there's a kind of underlying thread here, and I would like to ask to try to move towards having some sort of science of AI, and I think that causality is at the core of that. It is true that you could do, and there's more discussion here, maybe in the coffee break, even though I need to leave, but it is true that you could have cute airplanes before you have some kind of aeronautic type of engineering. And we pushed that for a few decades and kind of very cute and good results, but it did require some type of science of how to fly in order to put an airplane in 20,000 feet above the ground. I don't think that we are there in terms of AI. It's a kind of more cute, slightly clunky, but very exciting time that you can see the airplane or the AI start doing something. But I don't think that is, of course, and I will elaborate not only about scale, right? We need a science or something more fundamental about how to move from these cute Wright brothers or Santos Dumont folks that were able to do some kind of airplane in order to make the commercial airplane that you see today. In other words, I don't think that building it's like entertaining here, like more for, I don't think that building a thinking machine is easier, no easier than building a flying machine. And we are playing as a cute, let's do this thing in a more trial and error type of things, exactly as we did with airplanes. I'll share a link from a book. I discuss a little bit of history in the beginning of my book, textbook in causality. But anyhow, how do you move there? What is an insight from the area of causality? We would like in some kind of more formal way to model the agent-environment relationship and use some kind of causal language for that. We'll separate here these two concepts, the quote-unquote real world and the agent itself. Now there is some kind of interaction between these things. And the interaction will be modeled through formal language. And in particular, there are these three qualitatively different types of interactions between the agent and the environment. One is about we are kind of passively, let me see, where's my mouse here? Oh. You are kind of passively observing the world, and there's kind of sampling from there without any interventions. It's called observational data, most of the data today. I'll come back to that. The second one is about we are intervening in the world and seeing how things change eventually. And the other is like we are doing nothing, we're just sitting and kind of imagining different versions of reality, different counterfactuals, as we say. This is a quote from Turing. What we want is a machine that can learn from experience. Now the question is like, we like to ground experience. It's very beautiful, the poetry, but the question is like what experience means. My hypothesis that is, of people in the field is about it is related to grounding these different types of experiences. This is also acknowledged, a reference here called the Book of Why. If you have heard about that by Yuda Pearl and Dana McKenzie, and they call this structure the ladder of causation. They have this increasing refining from passively seeing the world, by intervening in the world, by doing, versus by imagining different versions of the world that may not exist at the moment. Now, just elaborating a little bit about what is this hierarchy, every time that you have a causal model that mathematicians don't shoot, I will not formally define here because it takes some time, but once a causal model for us will be a collection of mechanisms and a probability distribution over the exogenous conditions, over the border conditions, parts outside the model. And every time that you have a causal model, it's like we can consider physics as a causal model. Every time that you have a causal model, this induces this ladder of causation, which I call, this is this Bareinboim 2022, I call with Thomas Icard at Stanford and some of our students, we call the Pearl-causal hierarchy, just in honor of Pearl, given that he was the one that acknowledged that. Again, the layers here, just elaborating a little bit. The first layer is the one about associations, about seeing. The kind of question that humans will ask related to that is like, what would seeing X change my belief in the proposition Y? In machine learning, there is a counterpart, powerful counterpart for that is called supervised and unsupervised learning. All the formalisms that we have called Bayesian networks, decision trees, depending on the decade, you have a different one. Support vector machine, the deep neural nets, they are different language or different ways of implementing, ways of evaluating syntactically expressions like that, P of Y given X. It's true that at the moment you can have the X that is 1 million dimension. And the Y may be the next word, or maybe the label of the image and so on, the next frame. But still, we are trying to evaluate this probability distribution or function of this probability distribution. This is layer 1. Layer 2 is interventional. Syntactically, it also has a different type of signature. It looks like P of Y given do X, comma C. We kind of extend a little bit the language of probabilities to account for that. Do X means that we are doing the action. We are not passively observing the X at this level. What if I do X? What if I take the aspirin? Will my headache be cured? It's not that there is some kind of correlation between the aspirin taking and being okay without headache. There's a counterpart of that in machine learning as well that's called reinforcement learning that I mentioned earlier. Different languages to express knowledge, and once we express, then you have the corresponding inference tasks, causal Bayesian networks, MDPs, Markov decision processes, the partial observable PO, MDPs, and so on. POMDPs is called. And then you have the third layer, that is the counterfactual layer, that's called, is given by this type of syntactical symbol, very different than the previous ones. Note here that we have this X prime and Y prime. Everything that is after the conditioning bar, here is a mix. It's the notation. Everything in the first one is just that we are passively observing the event, big X, the random variable X is equal to this particular value, little x. But now we have the do X here. It's a mixed notation because this is observation, this is the intervention. This some people use, including me, depending on the day. This goes usually as a subscript to the probability distribution because we are indexing different probability distributions. And the notation may be a little bit funny. David Bly is here. Maybe he's sometimes like semicolon here instead of the conditioning. There's different notations, but the point is like this is operator, and there's different probability distributions here that we're talking about. It's not only one. It's a different type than Bayesian conditioning or Bayes conditioning. But here's a different beast, the third layer, that we have this big X is equal to X prime. Let's say Joe took the drug, that is X prime, and Joe, big Y is equal to Y prime, Joe is dead. This happened in the factual world. Now you can ask counterfactually, would Joe be alive? That is Y, that is the opposite of Y prime, had he not taken the drug that is X, that is different than X prime. It's a clean, cannot get more counterfactual than that. In the sense that, of course, we cannot do that in the world. Let's say that he died, then we cannot kind of bring him back from the other side. 1 millisecond before you give the drug, you submit him to the non-drug and kind of run the simulation, quote-unquote, and say simulation in the code of reality and see how things work. We cannot do that in general. Right? Then this is why it's called contrary to the factual world in some way. It's very related. Humans do all the time, very related to the idea of imagination or the concept of we are imagining these different realities. What could I have done differently? I didn't. But this may be giving very detailed, important information that can guide us in the future. Very related in the real world to the notions of blame, responsibility, credit assignment, and understanding in reality. There's no counterpart from that in the ML literature at the moment. Not doing paper review here in general, but it's not represented. It should be represented. the language that you can use to express that as a structural causal model. The formalization of the causal hierarchy, the PCH, provides a way to measure the capability or the expressiveness of different formalisms with respect to increasingly complex queries or types of questions. I'll defer here, but see, there is a result called causal hierarchy theorem. Yeah, I'll just leave the name for now. Some kind of impossibility result. The hierarchy, I don't know how many computer scientists we have in the room, but the analogous, the way that I like to think is when I was undergrad, we were doing formal theory and you do this Chomsky hierarchy that we're studying, I don't know, regular languages, context-sensitive languages, and you keep going up, Turing machines, right? Recursive, enumerable, and then here is the same, but in terms of understanding. You can kind of keep going up, and you can kind of more and more expressiveness in terms of understanding. And there is this CHT, the hierarchy theorem. It's not CLT, CHT, in some ways saying that this is more expressive than that, and this is more expressive than that. There is some kind of pumping lemma, if you are in the Talmud theory at some point, more complicated version of that, but there is some kind of, we can show that the languages are increasingly more expressive. Now, I would say, like, what is hard here? What's the issue, Elias? Because everything makes sense. Now I'd like to say the kind of inferences that we are interested is kind of different than the traditional ML inference. And different how? I just removed layer 3 here, but the same happened there. We can imagine and extrapolate. Extrapolation by generalization is very related to the layers as well. I digress. But here, the classical challenge here is about just think about layer 1 and layer 2. Most of the data available today is coming through perception, through the same, to passively observing the world unfolding and things happening. Elias' numbers, 99% of the data available in the world today that we have, huge amount, 99% is coming from layer 1. There's a tiny fraction that is coming from layer 2, I don't know, the FDA. Here in the US, decides to run these clinical trials. You spend, I don't know, $3 million, between $3, $5, $10 million to run a trial, and in reality, running a trial and having the whole machinery around, it means that you are able to sample from the layer 2 distribution. And it's quite complex in many settings to get data from layer 2, and sometimes even not realizable in terms of layer 3, despite it existing. But point being that most of the data is available coming back to layer 1, and most of the inferences about the world, or at least I would say interesting ones, are about layer 2 or layer 3. We would like to know effect of policies, treatment, decisions, and so on. Then the research question here, methodological or foundational, is how to use the data collected from passive observations that are coming from layer 1 to answer questions about interventions, decisions, policies, or even counterfactuals as well. But let's stick with layer 2 here. How is this possible in the world at all, right? Because note here, everyone is in the world of probabilities. I assume, let's call the distribution that you are sampling in layer 1, let's call that this is distribution P, probability distribution P. And in reality, we are trying to do the inference about layer 2, that's a probability distribution P prime. Then I have 1 million or 1 billion data points that are sampled from P. Our goal is to make a statement about P prime that maybe you have 0 data points. How on earth can you do that? Right? It's in principle, those are two disconnected objects. Now, I would like to frame that in terms of generative modeling here. Jacqueline and I were chatting before. I think it's an interesting topic, right? The Gen AI type of thing. How is this related to Gen AI? In principle, there is this belief that if it's generative, it means that it's causal in some way. And I would say it is the other way around. It's not an equivalence. If it's causal, if it's the physics or something like, we'll be able to generate things. But being able to generate it doesn't mean that it's causal. Let me elaborate a little bit on that. Let's say that we have the unobserved nature, that there is this causal model M star. The M star has the potential of generating the PCH, that is this bunch of probability distributions, layer 1 red, layer 2 yellow, and layer 3 green. That's great, well-defined, clean. But now reality kicks in, and we are unable to observe yellow and green. This is unobserved. Now I have a neural model, very big neural model, complex, need a cluster to run. In principle, it has the potential of generating these different things, because if it's complex enough, you can generate almost anything. Note here that I'm leaving it open, empty. Now you can use the data that we got, the red one, that is observational, to train this model. Sometimes it takes a week, a month, sometimes 6 months dancing around the cluster and making things to match. But I can do likelihood, we can do GANs, you can do diffusion, whatever method you have to fit the data. You fit, and eventually this guy, we wake up and, well, it fit. And then we're very happy. But the question, because it was a huge effort. But now the question is like, can you make any statement about the interventional, what would be the intervention, had we done the intervention in the world? But we didn't do it. We don't have yellow. Now, how is this possible? Now, this is called the fundamental problem. That is from the generative perspective. Under what conditions inference in M hat, that is in the right-hand side, are valid? In other words, when do they recover the distributions induced by the true M star that is in the left side? Of course, we can ask the same question for the layer 3. And of course, we can have little pieces here. We can do the same version of the problem. Maybe you have an agent, a reinforcement learning agent that is combining observations and experiments. And then you can ask about the green there on the other side. Then every time that you are matching perfectly and you have a question about red, and you get data from red, it's not simple. We spend a few decades trying to answer that, but still, I would say this is the normal in some sense. We are interested in the case about when I'm moving across colors, let's say, without having the color measure, quote-unquote color. Now, one example of a task that this could be applied related to layer 3, for example, just a cute one. I'm not a vision researcher, but just to show what would a person look like had they been ... For example, had they been 10 years older. Then you ask the AI to produce a human face, and then you get this face. And you say how the person will look like had they been 10 years older, and then we get this person that is kind of changing the gender as well. Or you say, give me a human face, you get this human face. The lady that is blonde, and then you ask what would happen had she be another gender, and then we get the guy, which seems consistent, but there's some kind of mismatch there, at least doesn't look the pair of the person. Right? It's a different age group, I guess. And I'll skip here gray hair just for the sake of time. This is kind of off in some way. We don't have guarantee for connecting the P and the P prime in a way. But now what's going on in reality is that there is some kind of, in the data set, there is some, in the top right there is some correlation between age and gender. It's not perfect, right? The balance between age and gender. As everything in the way, there's no perfect balance there. But of course, gender doesn't cause age, or age doesn't cause gender. Biological gender here for the sake of discussion. And age maybe also, but maybe have an effect on the gray hair. Age goes up, amount of gray hair goes up, probabilistically up to some point. Now, if you have causal, maybe you can get something. If you use this type of knowledge during the training process, you can get something like that, right? To get a human face, this seems to be the older version of the fellow. You get a lady, this seems to be the male version of her. Right? Seems even some sort of twin brother, and so on. Other implications for fairness that we're talking. Maybe you have this picture, this is from the literature, from the input, and then you ask, adding a little layer of language here, make them look like flight attendants, and then we're kind of changing the gender of one, because there's a correlation between type of jobs and gender, which is totally not expected, or not desirable, at least. Expected could be, or making them look like doctors, and then you change the gender of the other to become a male. Again, this is just based on the correlation between gender and job. Examples are all over the place. We can slice in many different ways. The correlation is the one that is driving and embedded in some way in the latent space. There are many other applications, I would say. I will not go in details, happy to discuss offline or give, sometimes I give the talks about that. The first one is about policy evaluation and fairness analysis. This is just the data that we run, that we get the data from the ICU, the intensive care in Australia. This is the map of Australia. You got the data of the whole Australia. This was amazing. Happy to talk with people that may have data. It was through a collaboration hard. They have the ICU admissions. Minority type there is the indigenous population. It's a highly non-trivial analysis there to run and kind of detect that there is some type of unfairness relative to this population. And then there is some type of policy recommendation where the government, and we are talking with the government, on where the government should be installing the hospitals. Minority population, given the discrimination, tends to be going to ICUs. This is a simplified version to solve basic problems. There's huge pressure in terms of cost, and it's totally unnecessary in some way. But anyhow, applications of fairness can be for health disparities that we're talking, can be criminal justice or environmental. Other kind of problem that you have decision-making way, this is more about explanations and understanding. The second column here is about decision-making. This is a case in kind of some type of cancer treatment related, my memory is right, to leukemia. This is some kind of sequential treatment, and the blue there is the outcome. And here, you are in the context of a trial, randomized trial. The red curve here is by Susan Murphy, kind of algorithm to do treatment allocation. There's some kind of way of doing randomization. Oh, this is the number of episodes, number of interactions, and this is the cumulative regret. Regret means oracle minus what the allocation procedure is doing. This is some kind, you would like to have something that is a log, something like that, that in the beginning there is some kind of exploration, and later you kind of learn what is the right policy, or treatment regime as it's called in the literature, in the medical literature. Now, this is Susan's, this is ours, which is good, and this is the one that we are leveraging layer 1 data, because this is layer 2. We are going there and doing the experiments and randomizing and deciding, you get the treatment 1, you get treatment 2. The green one is the one with observational data. When you have data that is biased by the physician, you can leverage this data, and the problem in reality is very easy, right? There is no regret here. Essentially, the scale is tough, but we do a little bit of experimentation in the beginning to remove the confounding, and later you can just exploit, quote unquote, in the language of RL. And the third one is about counterfactual explanations. That what I would say is like almost like how to open some kind of AI black box, and are you able to distinguish between the explanations, right? Or why the classifier, why the Gen AI is doing something in a particular way. I will skip that one just for the sake of time, but that's the idea. Very related not only to Gen AI, but algorithmic recourse, other kinds of technology in reality. About explanations in reality, if you go to philosophy or cognitive science, this is related to causation. Right? Lewis says that explanation is the way of, we are kind of tracing the causes that led to the particular event. The cognitive science says that humans like explanations that are more abnormal. Right? To have a fire, you can ask what led to the fire. Humans wouldn't say that it's the oxygen that is there. You prefer saying that there is the match. Does someone do something with the match, right? And then this kind of led to this spark that led to the fire. Of course, the oxygen was necessary in order to happen the fire. But then there is an interplay between causation and abnormality or normality that led to what is and other features that led to good explanations. Happy to elaborate or talk more. Now, what's our goal here? I'm almost done. The research program is to develop more general and trustworthy types of AI, endowed with the following capabilities: causal understanding and the ability of articulating explanations, being more efficient and precise in terms for decision making, more surgical. We don't want to have this quote unquote fat hand intervention, that there's a complex system and you put their hand and you do a big splash. You would like to be kind of surgical in a way. You would like them to be more generalizable and robust. You would like to have, I showed the example with the image, same to language, by the way. We like to do more causal and counterfactual type of generation, even though most of the data is from layer 1, from observations. And you like the model to do, Jacqueline is working on that, I believe that's learning and discovery, right? There's this field called structural learning or causal discovery that we are trying to learn about the structure of the world. And there is another one called causal disentanglement or representation learning that we are trying to learn what are the causal variables in the world. Many of the problems, if you are more in the sciences, you already know the variables. Many problems in machine learning, you have the representation challenge because we are getting data from different modalities, from pixels, from text, then the variables are not cut yet. Then it's an interesting problem. Both of them is this model learning and discovery. would like to share here. I start sharing maybe 1 week ago or 10 days ago is the first time that I shared. This is almost the beginning here. This is a textbook that I have been reading a few years that I'm teaching this class called Causal AI. You check it out. It's still draft, called causalaibook.net. Slides to come. It's kind of a very nice project. I'm very happy to be able to share after many years, and happy to talk about that. If you have instructors or happy to talk with students, share with your colleagues and so on. I'm still doing the slow profile here, and it's getting a lot of feedback and still changing. I change every week, by the way. If you don't read now, don't download it. Download 1 week from now, because every week I'm doing at least once a week a change, given the feedback that I'm receiving. There's typos and how this is huge collaboration. I'm just the one sharing here what we have accomplished, but thank you for the funding also from many people. And in the left is more my group at Columbia, and the right is the external collaborators. Happy to get questions. Thank you, guys. Yes.
Should I turn on
I think so. This is the instruction.
All right, great.
Let's follow the protocol, I guess.
Great talk, really thought-provoking.
Thank you.
I'll take your aspirin example as a showcase. When we say, oh, we take aspirin and then I don't have an headache anymore, most people won't count that as like a mechanistic understanding of what's going on there, right? I think it's kind of like relates to sort of levels of abstraction into like how can you say what does X do to cause Y? Is that something that like you've considered? And I guess the other part of it is that like different people will tell you different answers to this. If you ask like a cell biologist, they'll say something about how the T cells are interacting. A biochemist will tell you something about proteins that are binding and not binding.
Right.
What does that come into play in the Pearl hierarchy, and how do you think about something like
beautiful,
that?
beautiful. Thank you for the question. At the moment, let me do my advertisement. At the moment, everything that I talk here, in the formulas, there's this thing called the endogenous variables. Endogenous variable V, that is the variables that you observe at the moment, and all inferences are at the level of description of V. V1, V2, Vn. And a lot of the problems are done by the exogenous, variables that you don't measure. That's called U, unobserved, U1, U2, different type of unobserved. Unobserved, that's very peculiar in this case, or very specific in this case, that there is a variable U that is affecting more than one observed. Then I have V1, the aspirin and the headache, and maybe there is another thing that is confounding this relationship and making some people take the aspirin and some people get the headache, which is not causal. We like to know if it's the V1 that is affecting V2 or not this third guy, the age, the gender, the social, whatever other variables that could be in this case. But going back, then everything that I'm saying is operating at I said, or there's a claim, this is the level of abstraction that you operate in, V1, V2, Vk, Vn. But now there is another orthogonal dimension that I couldn't talk today, but it's very nice, very related to what you're saying, is about can you operate at different levels of descriptions? Can I kind of build abstractions on top of that? I don't remember the chapter, maybe chapter 15 or 16 in the book, but it's about causal abstractions, how you move across different levels of descriptions. Another example, depending on the case, we're on diet. Now, depending on the case, you're operating at the level of calories. But now calories is abstraction from the amount of carbs, fat, right, and protein in the world, or cholesterol. At some point in the literature, people talk about total cholesterol. This is a bad measure because in reality, we're combining LDL and HDL. They have completely opposite type of mechanism. Then the idea of moving across different levels of abstraction is kind of beautiful question. I would say not fully resolved, but we have there's a chapter there, and there's some kind of understanding about how to do that. And the punchline is like, it depends on which kind of inference do you want. Sometimes it's okay to operate on the calories. Sometimes you need to go to the other type of more fine grain. But how to navigate across this other kind of hierarchy, it's a topic of study. But thanks, beautiful, yeah. Yes, yeah.
I know in like observational causal inference, a assumptions that kind of need to be satisfied to like identify things in general. I'm guessing, or I'm curious about your thought on like in these super high dimensional scenarios, like I don't know, sequential decision making with a giant language model. Do you think that it's testable or like likely, or how to evaluate, I guess, that there are other things that could be making up for the lack of identifying assumptions being satisfied, like functional constraints or things, and sort of what is the right way to think about moving forward in these cases where we think that stuff is very likely not to hold, but perhaps we could be accidentally doing something smart, and is there a way to test that?
Yeah, beautiful. And I would say the question is in the frontier, right? I wouldn't say that we have a broader, full understanding about how to work when one way of paraphrasing the assumption, if I understood, is that which kind of statements can you make when the assumptions required for the inference we cannot ascertain them, right? It's hard to say that in general. I would say there is a good amount of recent work for the last few years, I guess 3 or so, that is related to a building block to answer the general answer is like doing some type of, not well defined, but let me use the word, some type of causal sensitivity analysis and try to understand the robustness of the conclusion relative to violation of assumption. This will be the dream or the very good way of doing that. Building block for that is growing literature. Literature on that is something called partial identification or bounding. That is exactly identification in reality is almost like a CLT, central, this is not CHT now, the hierarchy theorem, but the central limit theorem, or some kind of notion of consistency. Once the data is growing, I would say in layer 1, right, in the observational. If it grows, I have 0 data in layer 2, that is the intervention, but eventually things will converge. And we can discuss about which kind of convergence, but this is happening. This is what identifiability means. Now, but this means point identification, meaning it is converging in a very tight way. Now, once we have a non-identifiable case, the natural thing to do, and hard to gather results, but it's like, can you do some type of partial identification or bounding within certain interval? I know that my effect is within these bounds. Then how to do that in generality and scale, that's a technical challenge, but there are some kind of new results that I think could be exploited, could be built on to answer the general question in terms of language model at a crazy scale, right, at millions of variables. But I would say it's an interesting open question how to execute that. But I think you have some of the building blocks to start thinking about it.
And you would search partial identification for partial identifiability. What to search for?
A reference, yeah. I would say, I think section 5.6 in the book. You can drop me a line. And the book, apologies for not having it because it's new, and the book has, I think, 20 chapters or 21. And it's changing. Then I'm not. The other one is like a technical report. That's a paper in ICML a few years, 78 in my website. It's the paper that starts doing that. Yes.
One more, maybe short yes, no question. It's
yes.
A very interesting talk.
Thank you.
If I had a magical way of constraining the generative models I'm training to actually be causal, suppose I could do that. Seems intuitively that seems intuitively that I might need much less data to train them because there's a constraint.
Right.
Is there any theoretical or empirical support for that? That's the yes, no question. And you're out of time, so it can be just yes or no, and we can.
I say broadly no. Broadly it's open. I think it's.
Okay.
Yeah.
Thanks.
Thanks. Happy to talk more as usual. Yes. Hello.
I think my question is related to that challenge of scale.
I think you can click there. Yes. No, yes, this one I think is.
My question, is related to the challenge of scale that you'd mentioned before. I think one issue is sort of how to.
How are you? I think we met already. Yes.
Oh yeah.
Hello.
Yeah. Nice to meet you again. How do we sort of bring this like causal understanding to large scale systems? Because I think most of the literature, at least in causal discovery, and I'm not sure about the other areas of causality, has been focused on very small scale systems, and a lot of the methods they face this challenge of scale. So I was wondering if you have like.
Yeah, I don't think that we have a magical way of moving results to the large scale setting yet. The question is more, it's not even only that, it's about there is something special going on with language or vision. I show it's like a fragment of something in computer vision. But language or vision, we are moving to a different type of abstraction in some way. Then it's almost like things are happening in the, how the person will look like they being 10 years older, or this is happening at the factual, at the causal variable level, and you need to translate that to the pixels. Or you need to translate that to tokens and word in the text. And then there is some kind of tension between what's happening in the world and this level of description, of this related even more to the abstraction, with this type of abstractions. And tying that, it is I would say, work in progress. We don't have it fully tied. Of course, the dream would be, or one of the dreams, but I think a big one is like, can you have a causal, despite of the claims, I do believe that we are not there totally, but can you have some type of causal LLM that is LLM, that has some type of causal model? And we want to have despite of the power, this is my second video, this is very exciting, is a big soup. Right now, there's many models with many people that are describing stories and things about the world. And this is not how we operate. Level of precision and what can be done without a model stuff. Now, how to distill the model, how to nail that, unclear, right? But the first step is even to understand what is a model. Because otherwise, you're just in the soup, right? In the complete mess in some way. And the challenge of the mess is also related to the question of bounding apart. It's about, can you provide that will work in many cases? Yes, it can work. It's like, and we are accumulating data, and I don't think it will solve all the problems. But the questions about the stakes are very high. And we have mathematicians in the room. Can you, or computer scientists, can you provide any guarantee that the thing is not going completely off tangent or doing something crazy? And without a model, I think there is zero chance that you can provide a guarantee. You can put patch band-aids and patch things here and there, but provide a real guarantees that I think this should be the goal, one of the goals.
So something like finding the right level of abstraction and then also bounding the error rather than sort of going for a perfect.
And providing guarantees or some kind of certificate about we understand under what conditions something is happening. Right? It's not totally a dark magic type of emergency, full emergency type of thing.
Okay. Thank you.
Thank you. I'll take it offline, yes. Sounds good. Apologies.